An assertion made by Carlos Plain, an educator. I have committed myself to Durham School. My entire commitment is to facilitating an unambiguous speculation regarding the universe. At that point, this takes place. The rumors are being closely monitored. Because of this, I welcome the test. By looking at it this way, we advance and gain scientific ground. Thanks to the James Webb Space Telescope, we are essentially unsettling a few deeply ingrained convictions in cosmology that have long been deemed the truth. One more ultra-deep tracking image has shown that we have made blatant errors in space science. The telescope that was needed to truly represent the universe's focal stars has revealed a risky flaw in the previous perspective and introduced a brand new legal system. This perspective is not shared by all experts. However, pertaining to these new revelations, numerous experts have welcomed these levels of advancement. For a significant amount of time, it has been demonstrated that there were problems in our past hypotheses. The viewing peculiarities and the rate of the universe's advancement alone ought to have raised alarms a very long time ago. Instead, specialists definitively lowered the volume of these warnings, stuck to old theories about the background microwave radiation from the cosmos. The most out-of-date light is the CMB, cosmic microwave background. Around 380,000 years after the Big Bang, the universe had sufficiently subsided for electrons and protons to form stable hydrogen atoms. This process, known as reionization, created the universe we observe. The CMB was the first direct light recognized by the United States in 1964. Robert Wilson and Arnold Penzias, two physicists, encountered a steady clatter from every conceivable angle while working at the New Radio Authority. This discovery was initially considered solid evidence for the Big Bang hypothesis. Wilson and Penzias were awarded the Nobel Peace Prize, and their revelations became crucial to the foundation of space science. The CMB provides a brief examination of the early universe, with very low temperature changes that provide basic data about the circumstances shortly after the Big Bang. The CMB was utilized by analysts as a reliable marker for countless elements of the universe, including the rate of expansion. In the past, Edwin Hubble had made such assessments in the late 1920s. He observed massive systems moving away, and the relationship between their speed and distance is now referred to as the Hubble law. Despite the fact that Hubble's evaluations weren't as precise then as they are now, they were critical. The expansion rate was recalculated by experts, considering it to be substantially lower than Hubble's initial findings. Subsequent recalculations with the help of type Ia supernovae, rather than standard candles, provided better measurements. Nevertheless, mistakes persisted, and the difference in the rate of expansion, known since the 1990s, has been a point of contention. There have been rumors among experts about issues with the CMB's data analysis or the possibility of general enhancement errors. This individuality, known as the Hubble tension or S8 tension, suggests that our understanding of the universe could be fundamentally flawed. Then the James Webb Space Telescope, JWST, began its mission. Its tasks have produced impressive data that may assist in determining the nature of ancient galaxies, so old and mature that their growth might theoretically challenge what we believe about the beginning of the universe. Space science and long-standing theories now face what is thought to be the greatest crisis in contemporary cosmology. The acceleration of the universe and speculation about how it came to be are the subjects of shocking investigation. New images show a changing universe, and past models are being challenged. The S8 tension has become an early warning for professionals who still adhere to old hypotheses. Our current ability to interpret the universe might not be accurate. This flaw has affected numerous people. Inspectors are disappointed and even depressed, but we should be grateful. This is how science works, through speculation, tests, and refinements. Speculative scientists employ a combination of mathematical observations, data, and models to reach their conclusions. Seeing leads to understanding. Anomalies in test results and speculative investigation point to the nature of theory, not as fixed fact, but as evolving understanding. Images obtained through telescopes, radiation, sound waves, and gravitational waves are all data points. The JWST allows us to isolate light into individual frequencies and examine it in incredible depth. It can show what elements are present in vast systems that date back billions of years, how many people might have lived there, the mass of stars present, and more. However, Webb photos have limitations. It cannot see structures or black holes that influence light via gravity. Still, gravitational lensing has improved our understanding. New explanations are frequently proposed. Revelations made by JWST provide significant indicators that challenge previous hypotheses. We are now confronted with data that appears so out of the ordinary that tracking new explanations becomes critical. These discoveries are destroying the foundations of actual science and causing concern among experts. Current scientific guidelines are still influenced by Isaac Newton's 17th-century work. His laws of evolution and gravity formed the basis for comprehending the universe. These guidelines perform well under typical conditions on Earth, and even in space, they predicted expansion to an extraordinary extent. Albert Einstein's contributions, particularly his theory of relativity published in 1905 and general relativity in 1915, changed our understanding of space, time, and gravity. His theories demonstrated how mass could curve spacetime. Yet even Einstein observed the boundaries of his own theories and sought a unifying structure, something scientists still have not accomplished. It's fascinating to consider where the errors might lie. Michio Kaku, a well-known American physicist, suggested that this problem could lead to a Nobel Prize. We must examine all possibilities of reality. It's uncertain whether peculiarities have been misunderstood or if telescopes are flawed. Dark energy and dark matter are prominent players in the current cosmological crisis. According to current models, dark matter and dark energy account for roughly 95% of the universe. Yet they have neither been clearly demonstrated nor seen. They may not exist, or may have properties we don't yet understand. One possibility being explored is that the properties of dark matter might have evolved over time, possibly revealing some new understanding of gravity or mass interaction. The gravity of spacetime has not yet been definitively demonstrated to behave exactly as expected. This ongoing uncertainty opens the door to groundbreaking scientific revolutions. If gravity does not behave as we have long believed, if spacetime itself is more flexible or more dynamic under certain cosmic conditions, then we may be on the brink of rewriting the most fundamental laws of physics. Some theorists suggest that what we perceive as dark energy might not be a substance at all, but rather a misinterpretation of gravity's behavior over vast distances. Others propose that our standard model of particle physics is incomplete, lacking essential components that could help explain these cosmic discrepancies. In response to these challenges, international teams of researchers are collaborating across continents, using not only JWST but also instruments like the Vera C. Rubin Observatory and the upcoming Euclid mission. These tools are expected to deliver a flood of high-resolution data that could either confirm or dismantle current cosmological models. But the path forward is not without friction. Within the scientific community, some cling tightly to traditional frameworks, insisting that anomalies can be resolved with more refined measurements or slight theoretical adjustments. Others argue for bold, radical revisions, proposing entirely new paradigms of space, time, and matter. This intellectual tension is not a sign of failure, it is the essence of scientific progress. Every contradiction, every unexpected result, pushes us to refine our questions, strengthen our tools, and deepen our understanding of the universe. And in this sense, the crisis in cosmology is not a crisis at all, it is a renaissance. Meanwhile, the general public watches with curiosity and, at times, confusion. The sheer scale and complexity of these ideas can feel inaccessible. But the beauty of science is that it invites everyone to wonder, to explore, to question. We may not all grasp the equations, but we can all share in the awe of seeing ancient galaxies, bending spacetime, or witnessing light that has traveled across billions of years to reach us. The universe is speaking, and we are learning, little by little, how to listen better. In the end, whether the answers lie in modified gravity, evolving dark matter, or an entirely unknown force, one truth remains: the cosmos is not static. It is not simple. And our journey to understand it has only just begun. Einstein's idea of a spacetime twist has been supported numerous times. We are unable to completely dismiss the credibility that gravity possesses remarkable properties, or that an additional effect is causing the interaction of gravity over time. Explicit cosmological properties in space science have spread throughout, as reliable central constants are widely accepted, generally because of their regularity. Assessments indicate that variations in these constants may incorporate new information into our understanding of the universe, possibly grasping eccentricities without invoking dark energy. It's also possible that our perceptions of the absence of light movements have resulted in erroneous distance estimations, and that grandiose structures may challenge our presumptions regarding the universe. Either the conditions were unfavorable, or we misread the background of cosmic microwave radiation. It could be straightforward. Perhaps the universe did not begin with a single initial stage. Little is known about the Big Bang. Emissions from the Webb telescope or other observational tools make it impossible to rule out alternatives. Some experts and scientists in the field are aware that errors in instrumentation, data administration, or general comprehension are possible. The persistent re-evaluation of cosmological hypotheses highlights a principal nature of legitimate progress, the capacity to adapt and revise comprehension based on new evidence. James Webb's observations through space-based telescopes are more than just new innovations, they represent a significant step in our journey to decipher the mysteries of the universe. As we face these challenges, seeing the bigger picture is essential. Context and the consequences of reliable advancements in the field show that methods used in cosmology are frequently motivated by the need to improve hypotheses aligned with new insights. The elucidation of extraordinary anomalies or alterations in existing hypotheses can be disturbing, but it also provides a significant opportunity for legitimate scientific growth. The creation of hypothetical models in cosmology is designed to provide a framework for comprehending the universe's evolution since its inception. But as new data becomes available, these models ought to be evaluated and revised to accommodate emerging insights. One important focus area is what dark matter and dark energy are made of, both essential to modern cosmology. Dark matter is a subtle concept, a type of non-emitting material that doesn't absorb light, suggested as an explanation for discrepancies between observed galaxy rotations and the anticipated mass derived from visible matter. Dark energy was introduced to account for the observed accelerated expansion of the universe. Regardless, both dark energy and dark matter remain elusive. Earth-based investigations have, so far, failed to identify them directly. Researchers have thus relied on alternative approaches to investigate different hypotheses and possible causes. Understanding dark energy and dark matter is exacerbated by the enormous scale of cosmic research and observations of faraway galaxies. Background cosmic microwave radiation, together with other remarkable observations, reveals the existence of these components through indirect evidence. Despite their elusive nature, they remain crucial. This uncertainty has prompted scientists to consider a variety of hypotheses, from changes to existing models to entirely new laws of physics. Some hypotheses suggest particles that were not anticipated before, or that dark energy may signify a new fundamental force, an additional enticing subject of cosmological research. One area of active investigation is cosmic inflation. According to this theory, the universe experienced rapid growth in its early moments, leading to the vast-scale structure we now observe. The inflationary theory has successfully explained a number of features of the universe, including its uniformity and flatness. However, it also raises questions regarding how the inflationary period was structured. Ongoing observations that test established inflation models could result in changes to our interpretations. Finally, the universe's early history and the search for life on other planets continue to be major driving forces in the study of space. The discovery of exoplanets, planets that orbit stars outside our solar system, has opened new vistas to investigate the conditions necessary for life. Through telescope advancements, such as those seen in the James Webb Space Telescope, we can now investigate exoplanetary conditions, look for biomarkers, and explore the possibility of life. The significance of discovering life beyond Earth would have profound implications for how we interpret the universe and our place within it. In conclusion, the re-evaluation of theories about the cosmos is evidence of the efficacy of scientific inquiry. Instruments like the James Webb Space Telescope have offered incredible perspectives on the cosmos, causing researchers to re-examine and refine previous theories. This process of continual investigation and correction is essential for expanding our comprehension of the universe and addressing the fundamental issues at the foundation of cosmology and space research. As we continue to explore the universe, we must maintain our interest in research that not only seeks answers but also raises new questions, and motivates future generations to push the boundaries of human understanding. This unending pursuit of knowledge forms the backbone of our cosmic inquiry. Each new discovery not only deepens our understanding but also exposes the vastness of what remains unknown. From the subtle flickers of distant galaxies to the precise shifts in radiation patterns, the universe communicates in whispers, yet through advanced instrumentation, patient observation, and relentless curiosity, we are learning to listen. Collaborations across international space agencies, universities, and private institutions are becoming increasingly vital. The scale of data produced by observatories like the James Webb Space Telescope or upcoming missions such as the Nancy Grace Roman Space Telescope demands collective expertise. Artificial intelligence and machine learning now play crucial roles in parsing massive datasets, identifying patterns invisible to the human eye, and proposing new models that challenge even the most long-standing theories. As we refine our models and enhance our tools, cosmology evolves from speculation to structured understanding. The boundary between theoretical physics and observational astronomy becomes more fluid, driven by the synergy between abstract equations and tangible measurements. String theory, quantum gravity, and loop quantum cosmology, all once considered purely theoretical, now stand at the threshold of empirical testing, thanks to the clarity offered by modern instruments. One of the most profound implications of this progress is philosophical. As we peer deeper into the fabric of space-time, we are repeatedly reminded that our place in the cosmos is both insignificant and extraordinary. We are stardust with the ability to question its own origin, pattern, and future. The anthropic principle, suggesting that the universe's physical laws appear fine-tuned for life, reignites debates about purpose, coincidence, and multiverse. Meanwhile, the public's role in this journey is also transforming. Open-source data, citizen science platforms, and educational outreach mean that exploration is no longer confined to ivory towers or elite labs. Students, amateurs, and enthusiasts around the world can now contribute to discovering exoplanets, mapping galaxies, or decoding radio signals from deep space. And yet, even as we make monumental strides outward, we are reminded to look inward. Questions about sustainability, planetary protection, and ethical exploration rise alongside our ambitions. As we dream of terraforming Mars or mining asteroids, we must also ask, what values will we carry into the stars? What responsibilities do we bear as the only known conscious observers of this grand universe? The next decades promise extraordinary developments: quantum communication with distant spacecraft, gravitational wave mapping of black hole mergers, and perhaps even the detection of life on another world. But whatever awaits, the heart of cosmology will remain unchanged. A humble, relentless drive to understand where we came from, what we are part of, and where we are going.